Ever wondered why the CGS system still holds relevance in the scientific world? Well, let's dive right into it. The centimeter gram second, or CGS system, is a system of units that has been around for quite a while. Despite the widespread use of the International System of Units, or SI, the CGS system still holds its ground in several scientific fields. So what makes the CGS system special? To start with, it's characterized by its compact and coherent nature. This means that all derived units in the system are created from just three basic units: the centimeter, the gram, and the second. This simplicity makes the CGS system a favorite among many scientists. Take, for instance, mechanical quantities such as force and energy. In the CGS system, these are derived from the fundamental units of length, mass, and time. This is a stark contrast to other systems, where additional units are often introduced. One of the key aspects of the CGS system is its unit of force, known as the dyne. It's a small unit, much smaller than the Newton, which is used in the SI system. The dyne is defined as the force required to accelerate a 1 gram mass by 1 centimeter per second squared. Then there's the erg, the CGS unit of energy. 1 erg is the amount of work done when a force of 1 dyne is applied over a distance of 1 centimeter. It's a tiny unit, and it takes 10 million ergs to make up just 1 joule in the SI system. But despite its seemingly antiquated units, the CGS system continues to find relevance in the modern scientific world. It's often used in fields where its compactness and simplicity offer advantages over the SI system. So the CGS system's simplicity and compactness make it a favorite in the scientific community. It may be old, but it's far from obsolete. It's a testament to the fact that sometimes simplicity can indeed be the ultimate sophistication. Now let's delve into the core units of the CGS system. At the heart of the CGS system, we have two incredibly important units, dyne and erg. These represent force and energy, respectively. Let's begin with the dyne. The dyne is the unit of force in the CGS system. This unit is defined as the force required to accelerate a 1 gram mass by 1 centimeter per second squared. It's a rather small unit, especially when compared to the Newton, which is the unit of force in the International System of Units. To give you a better idea, 1 Newton is equivalent to 100,000 dynes. Yes, you heard it right, 100,000. Now, let's shift our attention to the erg. In the CGS system, the erg is the unit used to measure energy. Just as the dyne, the erg is also a very small unit. It is defined as the amount of work done when a force of 1 dyne is applied over a distance of 1 centimeter. To put it in perspective, it would take 10 million ergs to make up a single joule, the unit of energy in the International System of Units. A quick tip to remember these units: the dyne is to the Newton what the erg is to the joule. That is, both the dyne and the erg are much smaller than their counterparts in the International System of Units. So why does the CGS system use such small units? Well, it's all about keeping things simple and coherent. The smaller units allow for easier calculations and a more streamlined understanding of the physical world. So, in the CGS system, we measure force in dynes and energy in ergs. These small but mighty units form the backbone of this elegant system, enabling us to explore the mysteries of the universe in a simple and coherent way. Stay tuned as we continue to dive deeper into the world of the CGS system, its applications, and its enduring relevance in the world of science and engineering. It's time to explore where the CGS system is still in use today. The CGS system, with its compact and coherent units, may not be the go-to choice for everyday measurements, but it's far from obsolete. It continues to be favored in certain scientific domains, demonstrating its enduring relevance and utility. One such field is astronomy. When dealing with celestial objects and astronomical calculations, scientists often turn to CGS units. The reason? Well, the CGS system's smaller units can be more manageable and intuitively understandable when dealing with the vast distances and masses in astronomy. For instance, the astronomical unit of measurement for stellar luminosity is ergs per second. This allows astronomers to express enormous quantities in a more digestible manner. The CGS system also simplifies calculations. For example, when computing gravitational forces between celestial bodies, the use of CGS units leads to simpler, more elegant equations. This is especially handy when dealing with the complex computations that are part and parcel of exploring our universe. But the utility of the CGS system isn't confined to the cosmos. It's also used in the field of microphysics, where things are studied on a very small scale. Here, the small units of the CGS system are more appropriate and convenient. For instance, the sizes of atoms and molecules are usually expressed in angstroms, a unit derived from the centimeter. So, while the CGS system may seem antiquated compared to the more ubiquitous SI system, it still has a significant role in modern science. It's a testament to the fact that different systems of measurement, each with their own strengths, can coexist and cater to the diverse needs of various scientific disciplines. The CGS system, though replaced by the SI system for most practical applications, still holds its ground in certain scientific fields, and that's the beauty of science. It's a realm where old and new, simple and complex coexist and complement each other to unravel the mysteries of the universe. Stay tuned as we delve deeper into the fascinating world of units of measurement. The CGS system also has a special place in the field of electrostatics. Consider a world of charged particles, where electric fields and electric charges are the stars of the show. This is the realm of electrostatics, and here the CGS system, specifically its Gaussian variant, comes into play. Now, what makes Gaussian CGS stand out? It's all about the math. When you're juggling equations related to electric fields and charges, you want the process to be as smooth as possible. And that's exactly what Gaussian CGS does. It simplifies the equations, making them more elegant and concise. Let's delve a little deeper. In the Gaussian CGS system, the unit of charge is the stacoulomb, or ESU, short for electrostatic unit. This unit is based on the fundamental CGS units of centimeter, gram, and second. One stacoulomb is defined as the charge that, if placed 1 centimeter away from an equal charge, would experience a force of 1 dyne. Now, when it comes to electric field strength, the Gaussian CGS system uses the unit of stat volt per centimeter. This unit is directly related to the force experienced by a charged particle when it's in an electric field. In the Gaussian system, the Coulomb's law, which describes the force between two charges, is free of any proportionality constant. This makes the equations cleaner and easier to handle. Moreover, Maxwell's equations, which are the 4 fundamental laws of electromagnetism, take a simpler form in Gaussian units. This is why many physicists and electrical engineers still prefer to work with Gaussian CGS units when dealing with electrostatics. So, while the CGS system might seem a bit antiquated compared to the more widely used SI system, it still holds its ground in the field of electrostatics. The CGS system, especially the Gaussian variant, makes the math more elegant and concise in electrostatics. And in the world of science, elegance and simplicity are often the keys to understanding the complex phenomena that govern our universe. As we wrap up, let's summarize our journey through the CGS system. We began by exploring the key features of the CGS system, characterized by its compact and coherent nature. The simplicity of this system, where units for mechanical quantities like force and energy are derived from the fundamental units of length, mass, and time, is what makes it popular in scientific research. We delved into the units of force and energy in the CGS system. The dyne, which is the unit of force, is defined as the force required to accelerate a 1 gram mass by 1 centimeter per second squared. It's a smaller unit than the Newton in the International System of Units, but it fits perfectly within the CGS system. When it comes to energy, the CGS system uses the ERG. An erg is the work done when a force of 1 dyne is applied over a distance of 1 centimeter. It's a very small unit, with 10 million ergs making up 1 joule in the SI system. We also explored where the CGS system is still used today. Despite being replaced by the SI system for most practical applications, the CGS system holds its ground in certain fields of science. For instance, astronomers often favor CGS units when dealing with celestial objects and astronomical calculations. Lastly, we looked at the application of the CGS system in electrostatics. The Gaussian CGS system is commonly used in this field, simplifying equations related to electric fields and charges, making the math more elegant and concise. So while the CGS system may seem outdated, its simplicity and elegance still make it a valuable tool in specific scientific disciplines. It's a testament to the beauty of science, where different systems of measurement can coexist, each with their own unique advantages and applications. And with that, we come to the end of our journey through the CGS system. If you enjoyed this exploration and found it informative, don't forget to like the video and subscribe for more science, engineering, and much more. Thanks for watching, and see you in the next video.